So welcome back, everybody. The topic this week is a technical one, and it's essentially going to deal with gradient methods. And the question to you is, which gradient method should I use? So hopefully after this lecture, you're capable of seeing the wood for the trees. That's the hope. So if you now look at this flora or wealth of gradient methods, you may just ask yourself, which one should I actually use in project 1? And when you then move on to project 2, which one should I pick? So there are several methods. Methods like semi-Newton or quasi-Newton methods. Last week, we actually derived Newton's method. And what we did last week was to look at something which we just called the brute force gradient descent. And for those of you who may have taken a course in machine learning, you have already encountered the plane gradient descent. That is easy to implement, but it will depend on the learning rate. So one of the things which I will do today is to bring back a little bit of what we did last week, just to reboot your memories, and then bring back the codes which we need to write for this specific case. And for the specific case which we have here with very few parameters, then there is a method which is essentially the favorite method. And that's called Broyden-Farber-Goldberger-Shano, or BFGS. And that's the acronym which you will see when you use scientific Python, the optimized functions. And it's pretty straightforward to implement. And that is, and I will try to argue for why this is the preferred method. Then we have methods like steepest descent. We derived steepest descent last week. And then there is the more advanced method, which is called conjugate gradient descent. But all these methods, which you see there in the box number 2, they rely on you being able to calculate the second derivative of the energy. And that involves many Monte Carlo integrals. And that means that the second derivative can quickly become noisy with lots of errors and fluctuations between values. Then there is another method which is the favorite one in Monte Carlo calculations. And that's called stochastic reconfigurations. It was developed by an Italian condensed matter physicist, Sandro Sorella. He unfortunately passed away too early. And this is the method which we will discuss at the very end. But I would not recommend implementing this now, because that would require some more work. However, for project 2, you could actually have a specific path in project 2 where you implement stochastic reconfiguration. So that's a specific method, which is the favorite one when you do variational Monte Carlo calculations. But also, if you are interested in project 2 to solve the same problem with a neural network, then this is the way you would actually update the parameters of the wave function. So I will outline it here, but I don't recommend programming that for project number 1. So in project number 1, what I would typically recommend is that you either use plain brute force gradient descent. You can update that with momentum. You can use some optimizers like Adam, root mean square propagation, and so on, which many of you may have encountered when you took a course in machine learning. And the other one is to actually use the BFGS algorithm. Okay, so let me just put down on the whiteboard before we move on some of the technicalities and why these methods, which one of these methods we should use. So let me just switch to the whiteboard. And after that, I'm going to remind you a little bit of the things which we did last week, so that we can then, after that, we will move into the derivation of this semi or quasi-Newton methods, as they are normally called. So let's now just switch to the whiteboard. So the question is, which method are we going to use when we do the gradient descent? So let me quickly remind you of Newton's method. So what we did in last week, when we derived what's called Newton-Raphson, When we then, what we did was to take the function, a given function f, and this is now developed around some optimal parameter theta. And we are making an expansion around a variable delta theta, which is given by theta hat, which is the optimal, minus a theta n after n iterations. So typically what we will do then is that this theta hat is actually the optimal result after n+1 iterations. So what we typically want then is to find the roots of a given function. In our case, it's the roots of the gradients we want. We want to drive the gradient to 0. But let's just keep this function general, like here. And that means that we are making a Taylor expansion around this theta of n. So this is the previous value which we have, plus, and now I'm just putting this into parentheses. So we would have then plus, and then we have the gradient, delta of f of theta evaluated at the point n. And this is then multiplied. So this is now a vector. So we would have this transposed. Well, let's rather put it, since it's a vector, we just write it like this. And then this is multiplied. And since this is also a vector, we have a given set of parameters. In project 1, we have only one parameter. So that means that the gradient itself is just a derivative of the parameter alpha, as we called it. So that means that in our case, in project 1, life is much simpler. So when we do this Taylor expansion, we have the second order terms, plus, and then we have 1/2, and then we have this difference, theta minus the optimal value, and this is transposed. And then we have the second derivative. And the second derivative is something which is called the Hessian matrix. So this H is now the second derivative of f. And I just write it like that, and it is calculated at the value theta of n. And then this obviously is multiplied with theta minus theta n. And then we have higher order terms. So we have O, and then we have theta hat minus theta of n, and this is cubed. So these are the higher order terms. Now, to derive Newton's method, we truncate this Taylor expansion at the level of the second derivative. Okay? So when we truncate this at the level of the second derivative, then we end up with an equation. So truncating at the level of the second derivative then what we got then is an equation where we have theta hat, which is equal to theta of n+1. So we are happy after n+1 iterations. And then we have n minus, and then we have a parameter eta multiplied with the derivative of the function, which we are looking at, f of theta of n. And this is the derivative with respect to theta. Now, this eta parameter, which you see, is actually the second derivative. So this is then the inverse of the Hessian matrix. Sorry, let me just, I put it up, sorry for that, of n. And this is theta of n. So in the plane gradient descent, and this is the one which is implemented in the codes, in the lecture notes from last week. Then eta is just given by a constant. So that means that instead of having this as a function of n, so that means that eta of n is just equal to a constant eta. Alternatively, if we want to use the plain gradient descent, we can then have an update of the parameter eta. So we have updates of that parameter. The possible updates, if you want to use plain gradient descent, so in project number 1, you can actually use plain gradient descent if you want to. That's fully possible. I mean, we leave this to you. But then you have to be a little bit careful with the type of updates which you make. So you can have updates where you use momentum, for those of you who are familiar with that. So this is something which favors in a way those of you who have taken a course in machine learning. So we have root mean square propagation. We have Adagrad. We have Adams, and there are other methods as well. So these are all ways of updating this parameter eta. Okay, so this is one option which you can choose in project number 1. So if you want to, you can use plain gradient descent in finding the optimal parameter. Now, there's one thing you should keep in mind. For everything which we're going to do today, the function which we are going to optimize is the energy. We want to find the minimum of that. And when you have the minimum of the energy, the thing which is nice with the energy as a function of these parameters alpha is that the energy, essentially in all situations, is a convex function. That means that the second derivative is positive if you have just one variable. If it is a matrix, it is positive definite, which means that all the eigenvalues of the Hessian matrix are larger than 0. Okay? So in our case, we have to assume, and we actually can show that, we are not going to show that here, the energy is a convex function. It's going to be continuous as a function of the parameters alpha. So that means that the optimization methods which you're going to see here, actually all of them are going to work pretty well if you choose the right learning rate. This also applies to the quasi-Newton methods. So these methods here, which we call the family of plain gradient descent, these are methods where we actually take the parameter eta and replace the Hessian matrix. So we don't want to calculate the Hessian matrix. Now, methods like Broyden's method, the BFGS and Powell and so on, they try to approximate the Hessian by actually using what's called the second rule. So Broyden's method actually uses the second rule for the derivatives to find an iterative way of calculating the Hessian matrix without having to calculate it. So keep in mind now that the Hessian matrix, this object here, is the second derivative of your energy. Now, if you have 100 variational parameters, that matrix is a matrix of dimensionality 100 times 100. So it means that when you're looking at this iterative scheme for these parameters theta, there will be 100 values of theta. And if you then are doing 100 iterations, you would have to invert that matrix 100 times of a matrix of dimensionality 100 times 100. Okay, so this becomes quickly something which is complicated. And also, since I'm going to bring back the equation for the second derivative, this is something you don't want to evaluate in the Monte Carlo machinery. So this is basically one of the strategies which we can choose for this case. And the plain gradient descent with either the constant learning rate, but then you would have to tune it. So you would typically run calculations for the learning rate as a function of specific values. So you could take the learning rate 10 to the minus 4, 10 to the minus 3, and let it go up to 10 to the minus 1, for instance. And then you would make a calculation and see the one which gives you the lowest energy and which gives the best approximation to the gradients. Because the gradients will actually depend, I mean, the gradient descent which you're implementing depends on this learning rate. If you make it too large, you will jump out of the minimum, because what you're going to do then is typically something like this, just to remind you of what we discussed last week. So in our case, in project one, we have just one parameter. And we are calculating the energy as a functional of this parameter. And typically what we will get is something like this. And this is the optimal alpha, which we want to reach. Now, the reason why we do this, just to remind you of why, is that if we do the calculation in a very brute force way, like we have done till now, that means that every point which we calculated, like this, and then we would just find the minimum here by using some interpolation scheme. Every point here is a full Monte Carlo calculation. So if you're running a calculation with, let's say, 10 million Monte Carlo cycles, this point is 10 million evaluations, and so on. And clearly, if you have many parameters, this becomes expensive. So the whole idea with this gradient descent, which we are doing now, is that we are going to run fewer evaluations here, so that we can run, let's say, 10 to the 5 or perhaps 1 million instead of 10 or 100 millions. And then we find the optimal parameters. And when we have the optimal parameters, that's when we start the whole Monte Carlo machinery. Now, if you're having a learning rate which is too large, what could happen then? Suppose now you start with an alpha 0 here. So this is your first iteration. And then your gradient descent is going to bring you down here in the next step. So the gradient is actually always positive, negative as well. So it's going to bring you down towards the minimum. And if it's too large, so eta too large, what could happen then is that after this step, you may go here, and then you may go out of the region here, and your results will just diverge. If it's too small, on the other hand, what happens then, if it's too small, so let's just do that, too small. And if you're doing, let's say, 100 iterations, then you may move down here. And this is where you stop. So then it's too small. So the learning rate is something which you can tune in a brute force way by looking at the values of the gradients. And you would obviously always have, in these calculations here, you will always have a fixed number of iterations where you look at the value of the gradient. If that doesn't change, because ideally the gradient should be equal to 0. So you can look at, you can have as a convergence criterion, something like the norm 2 of theta of n plus 1 minus theta of n. These are the parameters which you have. If this is smaller than some parameter epsilon, then you will typically stop. So this is a typical stopping criterion which you would put in the gradient descent. And if you make the learning rate too small, you may not reach this stopping criterion. So this epsilon could be something like, let's say, 10 to the minus 4, or even smaller, 10 to the minus 5, etc. So this is actually you who decides how small it should be. And it depends also on the problem. Because in your case, you're going to evaluate gradients by Monte Carlo calculations. And I'm going to remind you quickly of that. Now, plain gradient descent is one way of doing it, because you have the gradients and you have the function itself, the energy. So in our case, what we have in this specific problem is the expectation value of the energy as a function of these parameters alpha, and the other parameter which we need to calculate is now these parameters, which is the gradient of the expectation value of the energy. So these are the two quantities which we need to deal with. Now, with few parameters, so the next step is with few parameters, with few theta. In our case, we call them label, with alpha, with theta being small. So keep in mind that theta is now a vector of a specific length of P. So that means that P is small. And small means something like less than 100, typically, less than 100 parameters. A typical Monte Carlo calculation is between something like a variational Monte Carlo, standard one, is something like 1 to 20 parameters, roughly. That's a typical variational Monte Carlo calculation. When this is small, when I mean small here, that means that the dimension of the vector, the length of the vector is small. Then what we can do is actually to use quasi-Newton methods. And the favorite one is the one which is called the Broyden, Farberg, and then it's Goldberg and Shano. That's the standard one which we normally recommend. But we have other methods which are also used, Broyden, Powell, and you will find many more actually. So these are methods which iteratively try to calculate the second derivative. So these methods here, many of them, not all of them, but typically what they do is they use the second rule. To approximate the second derivative. Derivatives. So if you think of Newton's function, Newton's method, you typically have a function f of x which you want to drive to 0. Then Newton's method in that specific case is just x of n plus 1 equal to x of n minus f of x of, this is Newton's method, where we just are looking after the roots of the function. So this is then the derivative of x of n. I'm going to remind you of that. This is Newton's method as it is implemented. In our case, this function is the gradient. We want the roots of the gradient, not the roots of the energy. So we are going to calculate, and that means that this function, which you see in the denominator here, has to be replaced by the second derivative. And that's the Hessian matrix, which causes all the problems for us. Now, if you look at the method as it stands, what you can do then, if you look at the derivatives, so you could then approximate the derivative at a given iteration. So that means that this f at x of n plus 1 is something which we can approximate with the function at x of n plus 1 minus x of, let me just rewrite this one on the next line so we get space here. So this would then be equal to f of x of n plus 1 minus f of x of n divided by x of n plus 1 minus x of n. This is just a second rule. So with that one, you can actually set up an iterative scheme which allows you to calculate these derivatives without evaluating the derivative. So if I'm using Newton's method, and you will see that in the slides pretty soon, if I use Newton's method, this guy is the Jacobian if we have more than one variable. If we have only one variable, this is a simple expression. But if we have more than one variable, this becomes a Jacobian. I'm going to remind you of that. And that means that you have to invert a matrix if you have more than one variable. That means that what you're trying to do then is to, instead of calculating a Jacobian, which involves several derivatives, you can then use the second rule for the derivatives. And this gives us Broyden's method. When we are looking at the second derivative, which is our case, because in our case, we are taking the gradient. And that means that this guy here is the second derivative of the energy. And that is a Hessian matrix. Then the method of choice is Broyden, Farberg, Goldberg, Shannon method. So in our case, if we now look at these methods, this would be the second choice. And this is normally the choice I would recommend using for project one. So you can do the gradient descent if you want to, but if you want to do that, you simply need to provide scientific Python or a library in C++ which implements the BFGS method. You would then simply have to provide it with your first derivative. That means the derivative of the energy. So you need a function which calculates the energy, and you need a function which calculates the derivative of the energy. And I'm going to show you the examples which I put up last week once again. So this is just, now we're just taking the bird's view on things so that you see what kind of methods would be the preferred ones. And these methods here are actually very stable, and in particular for our case, because our case is a case where the function is continuous and a convex function. So it's a well-defined and nice problem, which makes actually our life much easier. Then, if you're looking at the Monte Carlo methods per se, the favorite method then is something which is called stochastic reconfiguration, which we will discuss at the end of the lecture, at the next lecture. So we would then have the next class, which is stochastic reconfiguration, config. So this is discussed in the lecture this week, but I would recommend it as a project as a topic for project 2, commended for P2, and Variational Monte Carlo with neural networks. And I just write this NN here. That means that you replace your trial wave function with a neural network. And then you would have the parameters of the neural network. However, in that case, you typically have many parameters to fit. So if you do a neural network, let's say with 2 layers and 100 nodes in each layer, you would have typically 100,000 and more parameters to fit. So that means that your optimization with these kind of methods, which you see here, which we put up here, these methods, the quasi-Newton methods, cannot be applied because they become too expensive. And what you would do then is actually to go back to a plain gradient descent. And then you would do a plain gradient descent with updates like root mean square propagation, Adams, and you would use, instead of plain gradient descent, you would use a stochastic gradient descent. So this is just to see the basic strategies which we can implement. So in this specific case, what you would add would be SGD, stochastic gradient descent, with updates like Adams or similar. Because in this case, when you have neural networks, for instance, you have many more parameters than are feasible with the standard methods. However, if you're not doing a neural network, so I would say that this method which we see here, now what happened now? No, that's another lecture. This is the one I wanted. So if you look at this method here, what you could do for project number 2, you could only focus on that one as a modification of plain gradient descent or the quasi-Newton methods and make a comparison. So it requires a little bit more coding to implement the stochastic reconfiguration. And that's why I don't recommend doing that in project 1. So these are the kind of optimization methods which we end up dealing with when we are running these type of calculations. Any questions? I hope you see the wood for the trees a little bit better now. So what I wanted to remind you now is actually a little bit about the details of what we did last week. So let me bring that back to life here. So one thing which I wanted to remind you of before we look at the code is actually the expressions which we have for the first derivative and the second derivatives. So one of the things which we did last week was then to calculate the derivative of the energy with respect to these parameters alpha. And these are the standard equations which we have seen before. And when we calculated the derivatives, what we ended up with is this equation here. And this equation can be simplified by simply introducing the fact that this expression here, the derivative of the wave function with respect to the parameter alpha, divided by the wave function, can be written out as the derivative with respect to alpha of ln of psi alpha. Now, the reason why we like this form here is that many of the trial functions which we have are given by exponentials. So that means that we take the log of an exponential, and that often simplifies the numerics. So this is actually one thing, is that's a more compact expression, but it's also handy for us from a computational point of view, because many of the ansatses which we make, like the one in project 1, is given by an exponential with some arguments like x squared and so on. And that simplifies life. So the equation which we need to deal with, so the derivative of the energy, is actually given by these three integrals. This integral here, where this one is now given by the derivative with respect to alpha of the log wave function. And this is nothing but the covariance of this quantity. So this is the one we have to implement, the three integrals. And I showed you an example last week on how we can do that. Then I just wanted to quickly remind you of the second derivative. So when we calculate the second derivative, this is something which is going to be given by a series of integrals. So if we want to calculate the Hessian, we would actually need the derivatives with respect to beta and alpha, the second derivative, the general one, and that would be a matrix. So if I have 100 values, that matrix is 100 times 100 matrix. So it has 10,000 components and 10,000 derivatives, second derivatives. So you have to evaluate these guys here 10,000 times for every iteration. You don't want to do that, period. So now you see why calculating the Hessian matrix when you have many parameters is something which is not very feasible. For even one parameter, like you have in project 1, so in project 1, you would have the second derivative with respect to alpha. You still have to evaluate all these integrals. And it's easy then, with few integration points, that this becomes noisy. So that means that the second derivative you have in Newton's method is something you would like to avoid to calculate. So you see why we use these approximative methods? Okay, so this was a quick reminder of the equations which we did last week. And now I just wanted to remind you very quickly about the equations which we have to implement and how we can implement them. So if we then go back to the Jupyter notebook, and now I have to find my, let me just see here, just a moment. Here we are, too many windows open, as always. So this is the code which we went through last week. And then we looked at the case of 2 electrons in a harmonic oscillator trap. We implement these integrals. And here we have a trial wave function, which is a little bit different from the one we have now, because we have a so-called correlation part, which then is given by the exponential of the relative distance divided by 1 plus a new parameter times the relative distance. This is the wave function. I have an analytical expression for the local energy. I can then set up the derivatives of the wave function with respect to the variational parameters, as you can see here. So I have analytical expressions here. Now, what you would do when you have a more complicated wave function is to use automatic differentiation. So I strongly recommend using that, because that saves you a lot of time with the problems with derivatives, etc. Because it's easy when you calculate the derivative when you have the analytical expression and you feed it back into your code, it's easy to make small errors. So and you can set up the wave function, and then you can use the JAX to calculate the derivatives or automatic differentiation in C++ as well. It's called AutoDiff, the library. And that makes life a little bit easier when you're setting up all the derivatives. Now, the other elements which you see here are the same elements which we have been discussing before, the quantum force. The energy minimization here now computes also the derivatives, computing the derivative of the energy and the energy. So this does everything in one. So let me just quickly remind you of that. The formula which are relevant here, actually the calculation of the derivatives of the wave function, now of the energy. And here I have just implemented two variables, two parameters. And in my case, I then calculate the derivatives in an iterative way. This is done in a stupid way that you can see that there is no stopping criterion. I just set 100 iterations. I set a learning rate to 0.01, and this is then multiplied with the gradients, and this is how I update the parameters alpha and beta. So this is a very, how to say, brute force implementation of plain gradient descent with a fixed learning rate. So in this case here, if we run this code, it's not that slow actually, even though we have quite many iterations. So if you, sometimes that cheats me here, eh? Let's see. Okay, let's keep it running here. Then you can see now the calculations which we set up. You see the gradients are not exactly equal to 0 yet. So I could now try to increase this one. So as I said, there is no stopping criterion. And in my case here, I have something like 10,000 Monte Carlo samples. So I could rerun it with 100 iterations. We could just do that now. And while we look at the calculations with Broyden's method, this is actually the BFGS algorithm. Yeah.
Is it 10,000 per alpha?
Yeah, and beta. So this is the way I'm calculating the integrals for each alpha and each beta. And I'm doing something like 10 values for each, which means 100. And I'm trying to use that to find the minimum here. And that means that you would then run with only 10,000 parameters, 10,000 Monte Carlo cycles. And then when you have reached the minimum, if you're happy with this result, so you see now what I did was actually to calculate, to do this for 100 iterations. And if you're happy with this value, 10 to the minus 3, 10 to the minus 2 something, if that is the way we define 0 for the gradients, then we could say that, okay, these two values, 1.01 and 0.34, are the values which I'm going to use to run the big Monte Carlo calculator. So then you would say that now I am at the minimum, and these are the values which I want to use. However, if you're now using the BFGS method, this is more precise. And I would typically recommend doing that. So if you now take the same code, the only difference now is that I have one function for the energy derivative, because you need to provide with the SciPy functions a function for the energy. That's your function f. And then you need to provide a function for the derivative. And this is the same setup in the C++ program. So when you have that, what you would do then is simply to use this scientific Python library minimize, and then you use the BFGS method here to actually calculate the optimization. And this is what we are going to discuss now, soon after the break here. So you can see now that if you use this machinery, you set up a tolerance. You also have in this case, I mean, the number of iterations is by default, something like 50 or 40. I don't remember exactly what it is set up as a default. So I have the energy. I have an initial value for the parameters, which are fixed to 0.9 and 0.2. And then I provide the derivatives. And then I have a tolerance for the iteration here. which simply means that this is the kind of test which I make where I compare the parameters iteration by iteration. And if the difference between the new parameter and the previous one is less than 10 to the minus 4, then I stop. And you can see that here, I'm actually getting, if you now look at the results which I had, I get an energy, which is 2.99. I have a parameter alpha, which is 1.0, and one here, beta, which is 0.38. So if I go back and look at what my plane gradient descent gave me, you see it's not that different. But every time you run it, these parameters will be different. So what many people do then, if they run this in parallel and do, let's say, 10 different calculations, they will take the average of these parameters. And then the average of the energy, and say that the average of, let's say, 10 independent calculations are those which I'm going to use to launch the big calculation. And then you would keep the parameters fixed. You don't change them, but then you simply run millions and millions of Monte Carlo cycles. That's the basic recipe for doing this kind of calculations. So I would typically recommend here, when you have set up a function which calculates the energy and the derivatives, which is something you need to have, is to either implement your own plane gradient descent or simply use the minimization which is provided by Scientific Python. There is also a recipe in the lecture notes on how you would use C++. There is a library for C++ calculations where you can actually include the Broyden's method. Any questions so far? So this ingredient is something we need to have. And then next week, we are going to look at resampling methods, and that will also provide you with ingredients which we need to have in the calculation. Okay, so let's switch back to today's slides. So I just wanted to remind you then quickly about some of the technicalities which we have already discussed about Newton's method, but I'm going to discuss, after the break, I'm going to discuss Broyden's method and the BFFGS method. I'm probably going to skip Powell's. And if we get time, we will also say something about stochastic reconfiguration. Steepest descent is something which we discussed last week. So after the break now, I'm going to give you a quick reminder about Newton's method very quickly. And then we are going to jump into the derivation of Broyden's method and then the BFGS method, so that you have a kind of idea of how these methods are defined and what are the algorithms for doing that. And these are algorithms which are extremely simple to implement. So you could actually write your own function for them. It's not that difficult. The function is not longer than just some few 20, 30, 40 lines. Okay, so let's take a small break. So, but let's look at the basic details. So this is Newton's method. And if you then look at the basic method, this is what we end up with. So that's the equation which we are going to solve, and S is the root of the equation. We want to have f of S equal to 0. And then we keep iterating till we have reached the ideal. And that means to calculate the function evaluated at that value divided by the derivative. So that's Newton's method. In our case, this is replaced by the gradient divided by the second derivative. And then I just wanted to give you a quick reminder if you have two variables, because that shows you quickly the complexity of the problem. So if you have two variables, This is typically the functions you want to drive to zero as a function of x1 and x2. Last week, we had an example where we had a polynomial, which we then could rewrite in terms of a matrix times a vector which contained x1 and x2. In that specific case, the matrix stayed constant for every iteration. And then we could use the steepest descent method or the family of conjugate gradient method, because the second derivative or the first derivative do not change as we move on. It's the same matrix all the time. In our case, this is not the case. We are going to change the values of the second derivative and the first derivative iteration by iteration. And that means that the steepest descent and the conjugate gradient descent methods become inefficient because we have to evaluate the Hessian matrix or the Jacobian matrix and the Jacobian matrix. So if you do that, if you Taylor expand it, this is roughly what you would have, just plain reminder of multivariable analysis. And then you would define the Jacobian matrix. And that means that your equation then could be rewritten. You can rephrase Newton's method then in terms of the Jacobian here, where this one is actually the Jacobian times the function here. I guess you've seen something similar in your mathematics courses, right? So you see then the complication is that we have to calculate this one for every iteration. This is if we are dealing with the roots of the function f of x. We are interested in the roots of the gradients, and then clearly this function here becomes the second derivative. In that case, we need to compute the inverse of the Jacobian. So what I want to do now, there's a lot of stuff here. This is a little bit about the gradient descent methods. And these are things which you probably have seen in mathematics courses, so I will not remind you of these things. These are just some of the properties of the descent methods. And in our case, our function is convex. And it's continuous. And our second derivative is always positive. So let's now look at these quasi-Newton methods. And we're going to start with Broyden's method first, okay? So keep in mind now that what we want is the approximation to, in this specific case, we start with the derivative. And then we are going to take the next step, which is the BFGS method, where we're going to look at the second derivative. So let's switch to the whiteboard, because then there are some small technicalities which are worth looking at a slower pace. So what we're going to do now is just to look at Broyden's method. And if you have understood Broyden's method, the next step, the BFGS method, is actually just a slight complication of that one, where we focus on the second derivative. So let's now look at and define some steps which we will include in our calculation. So what we have is a function where we now have an iterative scheme where we have some k plus 1, which is equal to x of k minus some f of x of k divided by the first derivative of x of k. So I'm writing this in a generic way. These functions could represent vectors. This could be a Jacobian matrix, and this could also be a vector, right? But we're just going to try to keep the notation as simple as possible. So the question then is, how do we actually set up the calculation of this Jacobian matrix without calculating the Jacobian matrix? So let's now take a look at the derivatives. So I'm going to define some quantities, one which I'm going to define like s of k, and that is simply xk plus 1 minus x of k. And then I'm going to define a new function, which is y of k, which is f of x of k plus 1. Sorry, not uppercase f, but lowercase f, minus f of x of k. And then you know that we can define a function which we could now derive as a b of k plus 1 which is now the second. X of k plus 1 minus f of x of k divided by by xk plus 1 minus xk. And you see this is now just given by this y of k divided by s of k, with that notation which we introduced. So what we want is then also to find a function delta b, which is going to be given by bk plus 1 minus b of k. And one of the convergence criteria which we have is that the derivative should go to 0 when we have reached the minimum. And we want this delta b to be as small as possible. Now, if you look at the equations which we have here, if you take this equation which we have here, you see that we can rewrite this in the following way. So we would have a bk plus 1 times s of k equal to y of k. Now, the thing is that what we want to find now is an iterative way on how we can update this b of k plus 1. Because this is, after all, the gradient, right? So this is now going to define, if you look at the definition here, this is just the definition of the quantity which we will need in here. Okay? So this is just using the second rule. This is the basic approximation which we're going to do here. So what we want then, we want the following. So we want to have this b of k plus 1 multiplied with s of k equal to y of k, and that this delta b, which we have defined, which is a difference between the two derivatives minus b of k, is small, or ideally 0. So what we are going to do then, if we now write this equation out again, b of k plus 1 times s of k, this is nothing but b of k, the previous value which we have. So this is the previous derivative, plus this delta b multiplied with s of k equal to y of k. And we want that so that the function st, so that we can minimize this delta b. And what we're going to minimize is actually the Frobenius norm of that function. And I'm coming back to that one. So that's a constraint which we're going to set up. So let me come back to what the Frobenius norm of a function is. Have you seen that before, the Frobenius norm? I'm going to remind you of that because we can actually rewrite this one in a more compact way. So if I now isolate these terms, what I'm going to get then, if I look at these equations, so I have a delta b, if I isolate it, times s of k, that is equal to b of k plus 1 minus b of k times s of k. This is the same as y of k, as we have defined it, minus b of k, which we know, times this s of k, which we also know, and that is a residual. So this is this r of k. And so what we're going to set up now is to minimize the following problem. So these are just rewritings of the equations which we have. So we are going to minimize this Frobenius norm of the function. So we actually want to drive this delta b to 0. But to do that, since this is a matrix, remember now that this is the difference between the two derivatives. In principle, this is the difference between two Jacobian matrices. So this is also a matrix. So we want to minimize this one, f squared. And this is something which I'm going to show you now, which this is equal to the transpose, the trace of this quantity here. so that the delta B times this S of K is equal to this residual, which should be as small as possible. So let's now, let me say something about just let me remind you of the Frobenius norm of a matrix. So digression here. Frobenius norm, in case you have forgotten that one. So the Frobenius norm, when you write it out like this, if you take a matrix A with an F here, this is the same as the square root. And now I'm assuming that A is a matrix. It can be a real matrix. It could be a complex. It doesn't matter. It's an M times N matrix. And this is now a summation over I equal 1 up to N. So we're simply multiplying all the elements of the matrix. J equal 1 up to N of Aij squared. So the Frobenius norm squared is obviously just equal to A of F squared, which simply means that we take I equal 1 up to N, J equal 1 up to N, and then Aij squared. So if we then look at the matrix, we can actually, if you look at this expression here, the step is, how do we actually reach this expression? So keep in mind that what we want now is actually that these matrix elements, which are the matrix elements of this matrix delta B, should go to 0. They should be as small as possible, because we are taking the difference between, in this case, two Jacobians. Later, it's going to be two Hessian matrices. Okay, so let's just see that we can write it out like this, because that is going to give us an equation which we can solve with Lagrangian optimization, because we have a constraint. So there's a subject to a constraint that we want to have this delta B S of K equal to R of K, and we want to have that as small as possible. So we are going to translate this problem, which you see here, into a Lagrangian optimization problem, where this is a function we want to optimize subject to this constraint. Are you familiar with Lagrangian optimizations? So we are going to put that in a little bit later. But let's just see that this guy here is actually equal to the trace of the matrix A. So if I take the matrix A times T times A, if I look at that one, then this is a matrix, obviously, every one of these is a matrix of dimension m times n. So if I write out a specific coefficient j of k of that matrix, when I perform this multiplication, then what I'm going to get is the following. So this is going to be given by a sum of I equal 1 of m. And since we are transposing, it has to be Iij. This is a transpose matrix element, times Aik. If I take the trace of these guys here, then this is the same as the sum over j equal 1 up to n. So j runs up to n of At, because the matrix is now a matrix of dimension m times n. The transpose is then n times n. So these two matrices multiplied become a matrix of dimension n times n. So if I do that, then what I have is just this one, jj. And then I'm simply going to use this expression here. And then I can rewrite this one, because this one is nothing but a sum over I equal to 1. So this At A of jj is nothing but a sum of I up to n of Aij squared. So I'm just using this formula which you see here. So that means that my trace of At of A is actually equal to a sum over j equal 1 up to n, a sum of I equal 1 up to m, and then Aij squared. And this is nothing but the Frobenius norm of A squared. Okay, so where does that lead us to? Now that leads us to the following expression, that we can now add a Lagrangian multiplier because we have an optimization problem where we want to minimize this subject to this condition. So in order to achieve that, so this was a small digression. So now we go back. So we add a Lagrangian multiplier. And when we do that, we are going to optimize the following problem. We have this delta B, and we have a Lagrangian multiplier. And the function we want to optimize now is the trace of delta B transpose. So keep in mind now that this delta B is now the first derivative because we are just looking at the standard Newton method where we want the root of the function f. So this delta B is the difference between two Jacobians. And then I'm going to add, and I have a factor 2 lambda transpose. So this is now a vector. These are all vectors and matrices. So we have a delta B times the vector S of k minus this vector R of k. So we want to minimize, we want to drive this term here to 0. And we want obviously to minimize this one subject to this constraint. So this is a standard procedure where you actually use the Lagrangian formalism with a Lagrangian multiplier. And this is the parameter, the Lagrangian multiplier. So I'm not going to say more about the Lagrangian optimizations. So that means that what we want then is this with respect to delta B. And since these are matrices and vectors, we have to be a little bit careful. So this becomes simply 2 delta B when we take the trace, plus the next term, which is a 2 times lambda, and this transforms to SK transpose, which means that if I look at it, then this delta B is going to be equal minus lambda of SK of T. So when we then impose the constraint, which is this one. So we can actually feed that one back into the equation with delta B. We want that to be equal to 0. So what we find then is the following. If we impose a constraint, I'm just going to put it in the same page here. So if I impose the constraint, hope you can see that properly, delta B times S of k is then equal to minus lambda. And then I have an S of k transpose times S of k. I'm just multiplying, and that is the same as R of k. If I then bring everything in here, I can then define this lambda to be minus RK divided by SK transpose. If we just have one parameter, this is obviously just a scalar multiplied with another scalar. And that means that I can set up delta B, which is equal to RK, SK transpose divided by SK transpose times S of k. This gives me a new formula for BK plus 1, because we know that that is equal to BK plus delta B. So BK is my previous Jacobian. This is something I can rewrite as a BK plus. And now what I'm doing is actually to plug in this value for R of k. So I'm going to get an update scheme where I now have this Y of k minus B of k times S of k, SK transpose divided by SK transpose of SK. Now, the algorithm becomes unstable if this SK transpose times S is small. So that's a problem. This is Broyden's method. So I have a way now to calculate the gradient or the Jacobian without calculating the Jacobian. So what I'm doing then is simply that every value of this B of k, which I have. So if you now look at my definition of this quantity, so I have sk, this is the second rule. It means that my B of k, the previous value, is obviously k, and then I have -1, and here I have k and -1. So this is something which is much simpler to evaluate, because 1, I have this one, and 2, I have this one. So I have these values. So when I have these values, so you would typically start with an initial guess. You would then be able to calculate these values, and then you would have the first B of k, then you calculate the next one, etc., etc., etc. So these are quantities which we can evaluate by just starting with a previous derivative or a previous B of k. So this is the derivative, which we have estimated with a second rule. So this works extremely well if the denominator here is small, not small. And obviously, if this is a convex function, a continuous function is normally, it's a very efficient method of finding the minimum. Now, the BFGS method is a modification of this one for a problem where we need to calculate the Hessian. So if we now move on to the BFGS, basically the principle is much the same. It's a little bit more involved mathematics. So I'm just going to state the final result for the BFGS method, because now in this case, we are more tailoring things to the derivative of f of x, which we want to drive to 0. So that means that when we now look at these x's, and I'm skipping the vector signs, x plus, or k plus 1, is actually equal to xk minus, and now we have the Hessian matrix, the second derivative, times the derivative of f of x. So as I said, I'm skipping the vector signs here. So this quantity here is then proportional to the second derivatives of f of x of k. And this is inverse. So if we just have one variable, this is something which we could calculate. But if we have many, as is typical for a Monte Carlo calculation with many parameters, especially if you're replacing your wave function with a neural network, you're going to have tons of parameters. Then that means that this becomes a very involved set of quantities to calculate, and you want to avoid that one. Now, the basic philosophy here, it follows very much the same, which we had previously. So we are going to approximate this derivative. So our new B of k plus 1, which we had from Broyden's method, B of k plus 1, is actually going to be given by the gradient, which we have, of f of x of k plus 1 minus the gradient at x of k. And this is going to be divided by x of k plus 1 minus x of k. So the recipe for finding these equations is very much the same as before. So I'm going to skip some of these details, and I'm just going to set up the final expression for you. And the method which we end up with is actually, there's a slight modification, and you can find all the mathematical details in the slides, because I wanted also to spend some time on the stochastic reconfiguration as a final point. Now, so this is what we want to evaluate. And keep in mind now that what we want is actually the inverse of that one. So again, we would define our y of k as del f of x of k plus 1 minus del f x of k. So that's one of the points which we are going to set up. And then we are going to need this s of k, which is actually given by x of k plus 1 minus x of k. So let me just bring it back so you get time to write it down properly. Now, one important aspect with the quantities which we are going to look at is that our second derivative is always going to be positive. And we know that the energy is a convex function. And being a convex function means that there's going to be one minimum for each parameter alpha. You can actually show that for the energy. And then that means then that each second derivative has to be larger than or equal to zero, larger than zero. So if you take the second derivative as a matrix, that means that the matrix is positive definite and all eigenvalues of the second derivative matrix are going to be larger than zero. So that's a very important property. And in our case, we have a function which obeys these properties. So that means that all these methods, which you have seen now, they do actually work pretty well. The drawback which we have in the calculations is that these derivatives, the gradients which we have, they are given by the evaluation of free integrals. And that clearly leads to some stochastic noise in the calculations. So we are not going to have perfect derivatives. Except the case when you have the harmonic oscillator, where you actually have nice analytical expressions for the derivatives, which you could use to benchmark your Monte Carlo machinery with. So that's a very useful test. Okay, that's why I like the harmonic oscillator, because it allows us to perform all these tests here. Now, in this specific case, however, what we want is that this, if you look at this B of K, which we have defined, what we want is actually the inverse of that one. So we want the inverse and that's because what we are having is x plus 1 is equal to x of k minus h of k inverse, multiplied with a gradient of f of x of k. So when we previously had the equation b of k plus 1 of s of k equal to this y of k, what we are going to have now is actually an h of k plus 1. So we are going to replace that one, which is going to be given by y of k equal to s of k, because we want the inverse. Now, when we repeat much of the same recipe as we had before, we can then find that if we now treat this b of k as the second derivative, so inverting the inverse, yields the inverting the equations which we had previously. We can then find the following update. So we will then find that this b of k plus I is equal to b of k minus, and then we have b of k. So it's a little bit more convoluted, the expression, and you can find all the details in the lecture notes. B of k divided by s of k of t, b of k times s of k plus, so it's a little bit more convoluted. So these are outer products, so these are matrices, keep that in mind. And this is a y of t, no, y of k of t times s of k. And this equation which you see here, that satisfies this equation here. You can also show that this equation here leads to second derivatives, which are positive definite, etc., etc. So this is the formula which you see here. If we now frame it in, this is the famous BFGS algorithm for updating the second derivative. So what I'm going to do for the rest of the lecture is actually to bring up the algorithms which you can implement if you want to do it yourself. But I would typically recommend that you use these ready-made functions in different libraries. So Scientific Python in the optimization package has this minimization function where you simply either feed in BFGS, you can write the Powell's algorithm, you can write Broyden, etc., etc. So I just wanted to give you the kind of overview of possible methods. And the whole thing with the problem which we have is that typically when we have few parameters alpha, the BFGS works extremely well. And this is normally the method people would recommend in finding the optimal values. Now, if you dive into the weekly slides, you will also find much more material, but I don't have time to cover everything. So feel free to take a look at it. But let's now go back to the PDF file and take a look at both the algorithm. So let's just find the slides for this week. So if you just skip all this, because that contains many of these details which we went through. So you will find the final update function. And if you're going to implement this, so this is the BFGS Hessian update. And this Broyden family, it's normally called for that, is a one parameter set of second updates interpolating between rank 1, which is Broyden, and rank 2, which is then the second derivative, the updates. So the BFGS is a particular member chosen for strong numerical behavior. It often behaves very well. And in our case, the function, and you've seen that when you run calculation with the harmonic oscillator, it's a beautiful convex function. If it's not, you've done something wrong, period. And this is normally the BFGS. This is a kind of standard method for these kind of applications when you have few parameters alpha. It's also in case actually you have few parameters. Keep that in mind. If you're having many parameters, this becomes more inefficient. So if you look at Broyden's method, you can see here now an update of the algorithm. This is the update rule. You set up the equations for the initial points, and then you find the next point with x of k plus this p of k, which is your previous value. And then you define s of k, you define y of k because you found x of k plus 1. With that one, you can update the derivative, and then you continue. And typically what you would do then is till you reach the point where this function is equal to 0 to a given numerical precision. So this is tailored to you calculating the Jacobian, the first derivative. That's a typical implementation of Broyden's method. Then if you take the BFGS, we are having some input. So we calculate actually we make an estimate of the Hessian. And sometimes you just set it up by random values by requiring that it's just a positive definite matrix. This is what it means here. Then you start iterating. You have a search direction. Then you find a line search where you choose alpha k. You find the values of xk plus 1. Then you set these values. And then you find the derivatives, which is the difference between the two gradients. And then you update this h of k, which is your Hessian, with a BFGS formula. And then you stop when the gradient is getting close to 0. So these are the kind of very, very, how to say, central methods when you have few variables. And I would typically recommend that in project 1, you implement either the plain gradient descent with some ways to optimize the learning rate, or just keep a crude fixed learning rate and just tune it so that you get good results. Alternatively, to implement Broyden's method or the BFGS method. So this is also something which you can easily set up yourself if you want to, but I don't recommend it. Use those libraries which exist. The important thing is that you understand what is being done. So the essence is you use the second rule to find the derivatives. That's the starting point. And then you have an optimization problem where you want to drive the difference between the two derivatives to 0 with some constraints. And that was the basic recipe which we did with the Broyden's method, and the recipe for the BFGS method is not that different. Now, so These are the typical methods of choice. And these quasi-Newton methods, they build an effective linear response model from observation. And both replace expensive exact Jacobians or Hessians by learning curvature from the iterators. There are many other methods. So when you call this SciPy library, you will see that you have something which is called Nelder-Mead, you have Powell's method, etc., etc. So there is still space for you guys to come with a method named after you, if you cook up something which is efficient, and then you will be part of a library, if that is a goal in life. It means. Anyway, what I wanted to say something, I'm going to skip this with Powell's method. You can take a look at it. But I wanted to say, so this is also the steepest descent, which we went through last week. And essentially the function which we have to optimize, this is, if you think of the Taylor expansion we made, we discussed that last week. The Taylor expansion we made is actually around the optimal point. Is something which we can write like this. So this contains the gradients. So X is the gradient. And A is a fixed matrix. So if this is a fixed matrix, then the steepest descent or the conjugate gradient descent methods are viable methods. In our case, the matrix A, which is the Hessian, the second derivative, changes continuously. And these methods are not recommended. But if you wish to, you can look them up, because if you have let's say a polynomial, which means that you can rewrite a polynomial in terms of different variables, often with a fixed matrix, which does not change, then these are methods to be used. And you remember that last week, when we derived the method, we found that this parameter alpha here, this one, which plays the role of the learning rate, is then given by these residuals, and then the residuals times the matrix. And this is a method which is efficient if A does not change. But we know that the Hessian changes for every iteration. And then this is not recommended, because you would have to evaluate the Hessian. So I'm going to skip some of these methods. If we now look at some of them, if you look at, let's say, the gradient descent, the plane gradient descent, they're actually easy to implement. If it converges, it will converge a local minimal or energy function. In machine learning, which is often where you use these methods in ML, we're often dealing with extremely rugged landscapes with many local minima, and that can lead to poor performance. So for project 2, there is the option of replacing the wave function with a neural network. Then the neural network should have some of the basic physics, like the anti-symmetry. It should have something, if you're dealing with fermions. If you're dealing with bosons, it has to be symmetric. You have some translational invariance, some rotational invariance, if that's the case. And this is often much more difficult to fit, because then you have many more parameters. And they're sensitive to the initial conditions. All these methods are actually that. So there are many pros and cons. They are sometimes easy to implement. The gradients are computationally expensive to calculate for large data sets. So in project 2, this is one of the things you may have to face if you want to implement a neural network for solving the same type of problems. They're very sensitive to the choices of learning rates. And if you take a plane gradient descent with a fixed learning rate, it treats all directions in parameter space uniformly. So some of the variables may vary fast, and some may not. And that means that the plane gradient descent, unless you use something like an update of the learning rate, may actually converge poorly. So there are many pros and cons. They're easy to implement. The standard plane gradient descent is very easy to implement, because you just have this learning rate, and you need to calculate the You can also, and this is something which we don't have here in project 1, there are no saddle points. The energy is a nice smooth convex function. So the problems which you can encounter when you deal with neural networks, which is an alternative of Project 2, is the case of saddle points or local minima, which are not the right minima which we want to reach. So these are also other problems. And we will leave that till the second project. Now, I see I'm running out of time here. So I will rather pick this up next week. This is a technique which replaces the gradient descent, which we have discussed, with a method which is more tailored to the variational Monte machinery and the way of thinking. And it's called stochastic reconfiguration. And it was introduced by Sandro Sorella back in 93, 94. And this is something which is better than the plain gradient descent or even the BFGS methods. But I would not recommend implementing it because it takes a little bit more time. So this could be an option for the second project. So I'm just going to leave this as an aside, and I will pick it up next week and just go through the basic mathematics. And then we move into the resampling methods and how to estimate standard deviations in a good statistical way. And then we have the last element for the project by the end of next. And hopefully then probably we would have to extend the deadline a little bit so that we have a deadline till before the holidays. We put a deadline to March 20, but I think that can be a little bit tight. Yeah. And you know me, I mean, I'm pretty flexible with deadlines. Yeah. So the most important thing are the insights which we get. That's the most important thing. So we stop here, and then I pick this up next week. So hopefully you see this landscape of optimization methods, which in a certain sense is really at the heart of many of these methods. Especially if you go to machine learning, the optimization part is really the big thing. So this way to optimize the learning rate, which is called Adams, is a specific algorithm. That is a paper which has, and that tells you how important these things are in machine learning. So that paper, the method was introduced in 2014. And now, 12 years later, it has more than 200,000 citations. So a good scientific paper in most fields, when you reach 100 citations, you're very happy. When you have 200,000 in 12 years, that is orders of magnitude beyond a standard scientific paper. So that tells you about the importance of being able to speed up these optimization algorithms. Anything which can speed them up is something which will make you extremely popular. And you will get many new friends. And I'm not inferring that you don't have friends. These will be friends who will cite you. Okay, let's take a break here.